Okay, everyone, it's really, really exciting. This is our final exam review and the final video available for our class. Oh my goodness, it's all coming to an end. We're so close to being done. You guys have worked so hard, and I'm really proud of all of the work that you've put into this semester. I just want to say thank you for all of the work that you've done. And I know it's been a difficult course, but you've done so well. You've been putting in the work, and now it's finally time to bring it all together for our final exam review. Now, for our dynamics class, this exam is not cumulative. It does not cover every single thing that we've learned in this class. It only covers the last section of stuff that we've learned. So for us, that's going to be all of our planar kinetics for rigid bodies. Right, so this exam is just the planar kinetics stuff. Planar kinetics for rigid bodies. And this is what we talk about when I say over and over again. When we have things that are translating, bodies that are translating, bodies can be rotating about a fixed axis, or they can do general plane motion where they rotate and translate at the same time. And so the three main categories or the three main approaches to problems that we've talked about is that you can solve these problems by using your equations of motion. Equations of motion. So these were our forces and accelerations. So you have forces, linear acceleration or your angular acceleration. We also talked about moments a lot in this. So these were your equations of motion. We also talked about how to solve problems with work and energy. Work and energy, and when solving those problems, we were really dealing with forces, displacements, so your thetas and your s values, and then velocities, your linear and angular velocities. And then finally, we talked about our impulse and momentum. Impulse and momentum, and this is when we were dealing with forces, but we were also dealing with time, right? So instead of displacements, we were dealing with time with our velocity and angular velocity. So essentially, all we were doing is taking any of these planar kinetic problems where we have our forces, picking one of these three strategies to do, and then solving the problem. So we did a lot of different problem types, a lot of things like rolling without slipping, worked through many examples of this, but at the end of the day, they're all kind of the same concept, just applied in different ways. So when you're working through this exam, when you're working through your practice exam, just bear in mind that you can use any one of these for any problem and it should still give you the correct answer. It's just that some of these approaches work better for different problem types. So let's kind of go over each of those approaches again. We'll just kind of generally talk about how you can solve them, what you need to remember for these. And I would say for any of these, the biggest thing to remember, the biggest thing that's going to come up in every single one of these is your moment of inertia. So that moment of inertia that we've talked about a ton now, I value, moment of inertia, we had a few different ways of calculating it. Right, so one that comes up pretty frequently is when we're given that radius of gyration. So when you have that radius of gyration, that k value, you can use mk squared. And so that was a really nice one to kind of shortcut us from having to look anything up. Right, so we can have radius of gyration gives us moment of inertia. Otherwise, we generally look up our IG, our moment of inertia about that center of mass, from our tables. And of course, there's no tables given to you, or there's no back of the book that you can use on this exam. So I'd recommend knowing some of the more common ones or having those written down on your cheat sheet. So some of the more common ones that we see are when we have our slender rod. That's a pretty common one. If it rotates about its center, that's 1/12 ml squared. If you have a slender rod rotating about its end, 1/3 ml squared. If you have a disc, that's another popular one that we like to use. That's 1/2 mr squared. So I would recommend maybe going through some of those common shapes that we use in our moment of inertia and just writing some of those down, making sure that you know those. And so once you have your IG, you can also adapt your moment of inertia to any point by using your moment of inertia equals IG plus mass times d squared, where d is the distance from G to your point of interest. Right, so these are really your main like moment of inertia equations to kind of remember, understand the different moment of inertias, whether you're taking it at a different point, because they play a role in every single approach that you're going to do in every single problem in planar kinetics pretty much. Moment of inertia is involved in all of them. So if you don't have your moment of inertia down, it's really, really going to hurt you in these problems. So let's talk about them. Let's talk about our 3 methods that we've talked about for our solving problems in planar kinetics. And I will make a note here that we may or may not have gotten to our 3D kinetics at this point in the class. We might have enough time to kind of start looking at 3D kinetics problems, but I'm not going to test you on them at all. It's not going to be on this exam. We're not going to have a lot of time with them if we do get there. So don't worry about any 3D. These are only going to be 2D problems, planar kinetics problems, just using these 3 different application methods, whether you're using equations of motion, work of an energy, or impulse and momentum. And for each of these, we're not going to have any explicit kinematics problems either. So that was the chapter 16 stuff where we were looking at relative acceleration, relative velocity, instantaneous center of zero velocity, all of those types of things. There's not going to be any explicit problem about those, like just how to solve a kinematics problem, but they could appear as like little bits that you may need to solve one of these kinetics problems. So just bear in mind, you're going to get one of each, one that's solved really well with equations of motion, one that's solved well with equation of work and energy, one that's impulse and momentum. Right, these 3 categories, you're going to get one from each. So when we're thinking about problems that work well with our equations of motion and how we kind of approach those equations of motion problems, those are the ones where we said we were going to take the summation of all of our x forces equals mass times x acceleration. Summation of all of our y forces equals mass times y acceleration. And then we had a few different moment equations to choose from. We could take the moment about mg, about our center of mass, and that would equal our moment of inertia, g, times our angular acceleration. That was one option. We also said alternatively you could use the moment about any point on your free body diagram equals the moment about that same point on your kinetic diagram. And then we had a couple of special case moments. So we said the moment, if you're doing, for example, rotation about a fixed axis. If you're doing rotation about a fixed axis, you can take your moment about the fixed axis, and that equals I0 times alpha. Or if you're doing rolling without slipping, that was another special case that we had where if you take the moment about IC for rolling without slipping, that would be IIC times alpha. So we had several different moment equations that we could use. It was just a matter of picking which one worked best based on the actual problem. Translating, is it rotating, general plane motion, rolling without slipping. You know, understanding the motion of your problem and then selecting a moment equation that was going to help you the most. So when we had these equations, we could do it for translation. And again, our translation, our moment about g equals 0. We could do it for rotation, where we could use any of these first 3 here. And then our general plane motion, we could use pretty much any of these, but typically not this third one, but typically any of these other three. All right, so understanding the motion of these problems, and most importantly, setting up a free body diagram and your kinetic diagram. Right, so your free body diagram has all of the forces and the moments on it, and that's what gave us the left side of these equations, right? We would look at the free body diagram, we could pull everything from the free body diagram for those x forces, y forces, moments, straight off the diagram, pop them into the equation. Our kinetic diagram showed the directions of the accelerations. Right, so it had direction of your both linear and angular acceleration. And we could look at the kinetic diagram in order to set up the right side of the equation. So when we were doing those, we made two diagrams, looked at one for the left side, one for the right side, and it pretty much always gave us all of the information that we needed to solve the problem, right? To go ahead and plug into those equations to find what we were looking for. A couple of special cases to note when we were doing our equations of motion. One that came up for us a lot was friction. So friction was a special case where we could have something that is slipping or something that is not slipping. So if we're going through not slipping, so this is often with rolling without slipping, we have a couple of special rules that we can use. So one of those is that when we're rolling without slipping, AG equals alpha times R. That's one really handy thing to remember with our rolling without slipping. Another one is remembering where our instantaneous center of zero velocity is when we're rolling without slipping. And that is at the bottom where it's touching the floor there. Right, we can use that IC for rolling without slipping. Which also means we can use this moment equation, summation of moments about IC equals moment of inertia about IC times alpha. In terms of friction, if we have friction and we're trying to figure out if we're slipping or not slipping, when we're rolling without slipping, our friction has to be less than or equal to mu s times n. So that's our coefficient of static friction times the normal force. It has to be less than that. If it becomes greater than that, that's when it starts slipping. So we can tell if there is slipping, if yes, slipping. I don't even want to put this by IC because not. Let me put it over here. So if slipping, then the condition that we get is that F equals mu K times N. So that's our coefficient of kinetic friction times the normal force, and they're just equal to each other. Right, so that's true. That's the case if it is slipping. And if it's not slipping, then it stays in that static territory and below. So I know that it's kind of like a refresher from statics almost, rather than a true dynamics topic, but it's really important for a lot of these rolling problems that we could encounter. So just be aware that you may have friction and you may have rolling with slipping, you may have rolling without slipping, and that really changes how you approach the problem here. So that's a lot of what we dealt with our equations of motion, as we call them, or our force and acceleration problems. Then we also took a look at work and energy. And with work and energy, it was very similar to how we treated it as a particle, but our kinetic energy equation changed a little bit, and we did get one new form of work. So our new general kinetic energy equation, T for kinetic energy, is 1/2 mv squared plus 1/2 ig omega squared. So that's our new kinetic energy equation. Right, so if we have no linear velocity, maybe it's just an angular velocity, we wouldn't need the first part of this. Or if we're just translating, then we don't have an angular velocity, we wouldn't need the back half of this. It's totally situation dependent which aspects of this kinetic energy you actually need when you're solving your problems. And we also talked about work, right? So we talked about all of the forms of work that we could have, a lot of which we saw with a particle. So for example, we said if you have our most general form of the work equation, most general form of the work equation is if you integrate from S1 to S2 for that force over a distance. That's the general work equation, is force times distance. If you have a constant work, you can have F times S. If you have work done by weight, that's going to be your weight times delta Y. If you have work done by a spring, that's going to be, that's going to be negative 1/2 KS2 squared minus 1/2 KS1 squared. And then the new form of work that we introduced that we hadn't seen before was a moment. So if a moment is doing work, then we want to integrate it over the angle of change that it causes. So integral from θ1 to θ2 of the moment d theta. That theta has to be in radians, right? Because our moment is going to have the exact same units as the work. They're both a force times a distance. So whatever angle theta that it travels through, that's what determines the work that a moment does. And then other than that, the applications were pretty much the same as we had kind of seen in our particle applications, where we were using our principle of work and energy, which was T1 plus the sum of all of the work from 1 to 2 equals T2. And then we also had a lot of problems where we could use conservation of energy instead. So that's our T1 plus V1 equals T2 plus V2. Where our conservation of energy we can only use if only conservative forces do work, right? So no non-conservative forces are doing work when we use conservation of energy. So this means the only forces that can be doing work are going to be weight and springs. That's it. Those are our conservative forces. Those are pretty much the only ones you're going to be finding when we're using our conservation of energy equation. Where those V's, those potential energies, are still the same. They're either potential energy of your spring, which we said was 1/2 KS squared, or its potential energy from gravity, which is weight times Y, right? Or MGH is sometimes how you see it a lot. MGH are potential energy there. So again, these are really good methods to use when you have forces, distances, especially angles, since you have that moment that's going through an angle, and velocities and angular velocities. And the approach was relatively the same to how we did our approaches for our equations of motion, which was drawing a free body diagram and then drawing a kinematic diagram, drawing a diagram that showed all of the velocities with the directions of velocities. And so free body diagram with forces, kinematic diagram with directions of velocities. And then finally, go ahead and shoot that over. The most recent thing that we've done is our impulse and momentum. And our impulse and momentum was really very similar to how we treated it for a particle. We had our impulse, we said, is mass times velocity. Our momentum is going to be our angular momentum here, which is either r times m times v, or I'm sorry, not our impulse. This is our linear momentum, m times v. Then our angular momentum is r times m times v plus ig omega. Right? Those generally cover all of our different whether you have it with velocity or with angular velocity. It pretty much covers our angular momentum from different things in a body there. And so for this, we had our equations of impulse and momentum, sorry, our principle of impulse and momentum, I should say, where we used those three equations together to solve a problem, right? So that was mv1, sorry, mvgx1 plus the summation integrated from t1 to t2 of all of our forces in the x direction dt equals mvgx2. And we have the same for the y, mvgy1 plus the summation integrated from t1 to t2 of all of our y forces dt equals mvgy2. And then in combination with that, we had our angular setup. So that was ig omega 1 plus the summation from t1 to t2 of all of our moments about g, right? All of these need to be the moments of the same point. Mg dt equals ig omega 2. Those are for our angular velocities, our angular momentum there. And we were able to use these, apply these to problems, use these three equations together to solve any problems that we had in impulse and momentum. And then we also had our special case of impact and of conservation of momentum. So our conservation of momentum, we used our initial, sum of all of our initial angular momentums equals sum of all of our final angular momentums. And then for impact problems, we had coefficient of restitution also included in that. So that's our VB2 minus VA2 over VA1 minus VB1. So those are when we had impact problems where things were bouncing off of each other. Otherwise, if we had other types of collision problems, we were probably just using our conservation of momentum without a coefficient of restitution included. So all of these problems on this exam are all going to be truly on the same topic. It's all planar kinetics of rigid bodies. You just have different application methods that you can use. Right, so I'll give you, again, one problem of each, where one problem ideally uses one specific method to solve it, but hypothetically you can use any method to solve any of these problems. Whatever works for you. If you can get to a correct answer and show how you get there, that's full credit for you. So with all of that being said, this is going to be our last exam. This is all of our final content. We've done in this class all of our kinematics and kinetics of particles. Now we're wrapping up our kinetics of rigid bodies after doing our kinematics of rigid bodies here. And that's it. That's the whole course. I know you guys have worked so hard to learn this. Dynamics is not an easy topic, but I really hope that putting in this work and preparing for these exams, preparing for this coursework, going through all of this coursework will really help make you a better student, prepare you for when you go to university and do your higher level engineering classes. You know, some of this stuff will come back. It may have different applications in different courses, maybe applications in your future work. And so I really hope that it helped you, even if it felt like it was a lot of work and a lot to learn. I really hope that you were able to take something away from this course, and at the very least maybe take something away about how you learn, how you study in this class, and how you can take that forward and study for your more difficult engineering classes in the future. But all I want to say really is thank you. Thank you for all of the work that you've put in. Thank you for taking this class with me. It's been a really great semester, and I hope you guys have a wonderful, wonderful break. And enjoy your transfer university if you are transferring on. If not, I hope I get to see you again at Oakton sometime. Good luck, and I hope to see you soon.